Okay, here's our second lesson on exponential functions. If you recall, the exponential function looks like this: y equals b to the x power. Now this is decent in terms of what describing exponential functions initially. However, to actually make them useful, we have to derive a few equations or memorize a few equations to use. So here's the exponential growth and decay models as sometimes they're used in real life. Note some things about this. This is still very much like that form, y equals b to the x, except our b is going to be this 1 plus r. This is for adding a certain percent annually to a given amount. I've got that stated right here. So what this little formula does basically is it takes the entire amount that you're talking about. Say you put in $100 into the bank, and you got some interest rate on it, let's say 30%, so 0.3. So what this model does is takes your amount times 1, because in the bank you're going to keep that $100. Plus, though, you add on this 30% of it. So this 1 plus the rate gives you the whole amount plus the extra because of the percent. And then the t is how many times they're going to add that percent to it. This formula here is for a increasing or decreasing by a constant amount each year. Some other time period you could use, but then your rate would have to be adjusted correspondingly. So if they did tell you, we're going to give you 3% per month, then this t would be in months. So A is the initial amount, R is your percent rate that they're giving you as a decimal, though, and then T is the number of years. When we do that 1 plus the rate they're giving you, that's called the growth factor. If we do 1 minus the rate, it'll turn out to be 1 minus some decimal, so you end up with something less than 1 here, which forces it to be decay. What this function does is it takes the whole amount, but it subtracts off the percent it's decreased by. So it would take away 20%, for example. 1 minus 20%, 0.2 would give you 0.8 right here, which would be a decay. So let's go ahead and apply this to some problems here. So you put money into the bank. They promise you 3% annually of interest if you put in $100. Okay, so you're going to put it in there for 40 years. Let's see how much you will have. Initial amount, that's your A value. You're putting in $100. You're going to grow at 3%. Now remember, this is 3%, which is 3 per 100, which is 0.03. It means, move your decimal 2 spots to change that percent into a decimal value. So that's our growth rate, 0.03. And then the growth factor, the actual number we're going to end up putting into this is 1 plus that growth rate, so 1.03. So our equation, y, the amount you're going to end up with, is the $100 times 1.03 to the t power. We're going to do this for 40 years. You can see I've got my calculator open, obviously. And so the way you enter this is the 1. Let's try again. The 1.03, the y to the button, and I'll type in 40. So I take care of my exponent first, and then I take it times 100. Do the multiplication last, and I get $326.20. Remember, this is an amount. So you take your $100, just let it sit there for 40 years. That's how much you end up with. Let's see what happens if we do it if you could get a better interest rate, 10%. Okay, y equals. And there's certain ways you can save your money to get that. Now, our growth rate changed. We were at 3%, now we're at 10, so that is 0.10. Again, move your decimal 2 spots to the left. Then we have to add the 1 to it, so 1.10, that's our 1 plus r to the 40th power. 1.1, and we'll raise that to the 40th power, and we'll take that times 100. So 7% more, 10%, from 3 to 10% gets you way more for your money. So 10%, even though it's only a 7% jump from the 3%, we get way more than a 7% increase over those 40 years. Let's go ahead and do a decay problem here. In this decay problem, we've already given you the equation for it. There's the equation, y equals. Now this is the cost of a car in thousands of dollars, so this is 25,000 right here, but we can just put 25, knowing that it's in thousands. You can see it's going to decay because this 0.85, that's less than 1, so it's a decaying function. And t is the number of years. So tell whether this represents growth or decay. Well, we can tell right away this is decay because of the 0.85. Find the percent decrease since it's a decay. So remember this formula, y equals a times 1 minus r raised to the t for decay. So this 0.85 in here, that must be 1 minus r. So 1 minus r must equal the 0.85. Now you could do it by inspection and just look at it and just go, well, 1 minus 0.15, 0.15 is 85. That'd be the way to just kind of think about it and solve it. Or you could subtract 1 from both sides and you'll get negative r equals negative 0.15 and divide by negative 1. Regardless, the rate is 0.15 rather, but as a percent, that would be 15%. So this car goes down by 15% each year, which means it's worth 85% each year of its original value. So let's estimate when the car will be worth $8,000. So in our function, y equals 25 times 0.85t, in this function, we want to figure out when the value of the car is 8,000. Now, we don't have to put 8,000 there. We just have to put 8. And we have to solve this for t. Now, we do not know how to solve an exponential equation yet. Doesn't mean we can't do it, though. We can still graph this equation. So let's take a look at him here. Didn't want that. I'd like to see my equations. There they are. And that is the one I have highlighted right there. Y equals 25 times 0.85 to the t. So the graph is shown here. So you can see at the very beginning, that's going to be our y-intercept. At 0, 25, that means when time's 0, the car's new, no time's gone by, it's worth $25,000, the original amount. And as I trace this graph, hopefully, there we go, you'll start to see some of the other values. So after 3.8 years, it's worth $13,000. Now we're looking for 8,000, so I'm just scrolling here. There we go. 8,000, 6.8 years about. So estimate when it will be. I'm going to estimate approximately 7 years would be a good answer for that. Next example, population. We start with, in 2000, 6.09 billion people. During the next 13 years, it keeps going up by 1.18%. Let's write a model in billions for t years after 2000. So our raw model, this is growth clearly, is 1 plus your rate to the t. How much do we start with? We started with 6.09 billion times 1 plus, what's our growth rate? Well, our percent is 1.18%. So when we move this 2, it's 0.0118. So 0.0118 to the t power, or 6.09 times 1.0118 to the t. and that will predict your population. And there is answer A. Figure out what the population will be in 2021, so we'll go y equals 6.09. We just have to figure out what time to put in. Well, this is started in 2000 when the population was 6.09, and now it's 2021, so that's 21 years later. So 21 years it's going to grow at this rate. And again, this is a calculator problem. Let's get this guy out. I'm going to type in 1.0118. I'm going to raise it to the 21 power. Then I'm going to take it times 6.09. And that means right now, in 2021, the population should be about 7.79 billion people. So over 7 billion, and then in question C here, estimate when it was 7. So it's going to be less than 21 years. So again, we're just going to graph this thing. I think I had him already on here as well. There he is. So here's what it looks like, that growth function. See, if I zoom out, it is exponential growth. We don't have to go that far out though. Here is our y-intercept. When time 0 in 2000, it was 6.09 billion people, and we want to find out when it's going to be 7. So I'm just going to walk along this graph, I hope. Let's see if I can, there we go. 7 would be 6.6 years. So somewhere between 2006 and 2007, it was at 7 billion. And that's it, everybody. We did not get to compound interest in this unit. Your homework is actually a Google form, so make sure you go into this date. This was on, Friday the 7th, I think, May 7th. On that date, you'll see it's a Google form. So fill out the Google form and submit that.